Hello, everyone. My name is Walid Hakoum, and I'll be talking about my final project, and it'll be about the center of mass of random boundaries of an enclosed shape that was that is surrounded by random boundaries, and it is with Dr. Kinder. So let's get started. So first, I'm going to talk about the equations that I used to determine the center of mass and the area, and the boundaries, and what were the limitations of the boundaries, and what troubles that I've encountered through the process of selecting the boundaries, and the methods that mathematical methods that I used to implement that in Python. So for the boundaries, I started with actually very complex functions. They don't seem very complex, but sinusoidal functions were actually very complex. With this, I did not know this until I actually tried it, because it was unpredictable to figure out where exactly they would meet, and for the bisection method, because that's what I was using uh, to um, um, to find the root of these two functions, where these two functions meet. Like, for example, for these two functions, they would meet right here, and this would be at 0 0, and this would be at about negative 2.2 or 2.4 and 2.1 probably. And for the bisection method to work, you have to select an exact uh, or a range. You have to determine a range for every possible scenario that would work on every possible scenario. And that was very hard to accomplish with sinusoidal functions, because they were, well, first, there's a lot of roots. There would be a lot of roots for these two functions. This is just sine and cosine. And you can see that there's one here, and then one here, and then one here. They would meet every, like, twice a period, or even more than that. So it wasn't really possible, or maybe it would be possible for me to do, but my I'm not very expert on Python, and um, I honestly just couldn't think of a way to accomplish this. So I moved on to exponential functions, and I said maybe if I can make one that is set to be negative, or even I changed it to negative parabola, and then I would use the other function, just x to the even power times e to the x, and that would give this red shape, which actually worked a couple of times. But as you run the code for a large number of times, that would not work. And it was easiest for me to just use parabolas, negative parabola and positive parabola, just to illustrate the principle. So these are the shapes that would come out if you use negative parabola and positive parabola. And now, when I say negative and positive parabolas, that means that I would have f of x to be um, negative parabola, of course, but it wouldn't be an actual parabola. It would just be x to the to an even number, to a randomly selected even number, and it would be shifted up, and it would be shifted on the y-axis, on the positive y direction, by a randomly selected value. And same goes for g of x, just the exact opposite. It would be a positive parabola, and it would be shifted downward, just so they would meet in a predictable range. So the bisection method would work. This was actually the hardest part of my project, is making sure that selecting the boundaries would make would make the bisection method work. So the way bisection method work is if you have, for example, this curve here, and you want to determine the root. Now the root, if you have one function, if you want to find the root of it, that means where it intersects with the x-axis. So you select just a random two numbers, like for this example, a1 and b1, and then you plug them into the equation, and you get f of a1 and f of b1. And after that, you get the average, which would result in this case probably be a3, like right here maybe. And then after that, you have to select opposite values or values and opposite signs for the x values. So for example, here we would have b1 as a negative value, and the average would be positive value. So we would use a3 and b1 in this example, because, well, actually it would be b2. Yeah, b2 in this example, and a1, because they're opposite in sign. This means that there is a root somewhere in between these two x values. And you keep doing that over and over and over until you get closer and closer. Like if you take the average between a1 and b2, it would give you a2, and you would plug it in. You would plug it in, and you would get a positive value, and you would get the average between a2 and b2, and it would give you a3, and it would be positive. And then you would plug it in again, and you get a positive value, and so on and so on and so on until you get very close. Now, probably you have a better picture of why this did not work with me here. Because say if I selected 5, like for the first root, -5 and 5, or 0, -5 and 0, and for the other root it would be 0 and 5, for example. Now this would work in this scenario here, but in other functions it would not work, because the like I said, the functions are going to be randomly selected, and the boundaries are going to be different every time, and it was really hard for me to determine one range for every possible scenario. And then after that would give me actually the answer to this. So the root of f of x minus g of x would give me where these two functions would meet, and then I would plug in a and b as the root 1 or root 2 in a numerical integration method called the trapezoidal method to get the integration of this function in that interval in between these two roots to get the area of the whole shape. And now just a little bit, let's go over a little bit about like what trapezoidal method mean. It's actually very simple. If you have a shape and you want to get the area under a curve on a specific interval, let's say between xi here and xn, this last red or orange line here. And so if you cut this, if you divide this section or interval into equal sections, and then you get just on the x-axis, and you plug in these x values, and you get the values of this, and now you have xi plus 1, and then xi plus 2, xi plus 3, and so on and so on, and you would get the corresponding y values of these x values. And after you do that, you just calculate the area of one trapezoid, which is the average of the two bases times times the height, which is in this case xi minus or xi plus 1 minus xi. So it's just how wide this. In this case, it will be p. And then you add these areas together, and that would give you an approximated value for the area under that curve. And obviously, the more trapezoids you use, meaning the more sections you want to cut under this curve, and do this using simulation or computer simulation like Python or MATLAB, it would be very accurate actually. Like it would be in a very high precision, the value that you want to get. So let's look at the code and look at how it works. So now I have here the bisection method and the trapezoidal method. I put each of them in a separate function just so I would plug them in whenever I want. And then I used a for loop for just selecting only even numbers for the powers of x for the parabolas. And then this would be the roots function. This is just I wanted to set the function equal or equal to each other and solve for x to get the roots where these two functions meet. And the way to do that is just subtract them from each other and equal them to 0 and solve for x. So that's what the roots function does. And I would later on plug it into the bisection method to actually get the root with this precision. So it would actually be very precise. And this is the equation for the x coordinate, and this is the equation for the y coordinate. Now let's try it. So this is the f of x, and this is the g of x, and this is where they would meet. This is the area, 12.154, and this is the x coordinate and y coordinate of the center of mass. And you would actually get a different shape every time. This could be updated or upgraded in a very interesting way. It was just my limited knowledge about Python prevented me from doing that.